What is artificial intelligence? Come on, help me out, folks.
I might just a fast way to manipulate very large sets of data
Okay.
and utilize that to answer questions.
So a way to analyze or process large amounts of data and answer questions. So sure, that could be part of it. Any other ideas about what artificial intelligence is? Don't make me call on people. Come on. I'm gonna have to get back my teacher role. Mason, what's artificial intelligence? Saw it coming, right?
Yeah, I would say that it's artificial intelligence is technology which uses machine learning. So like the computer programs which can learn from their data sets, which are updated usually with very large data sets.
Okay, so a kind of component of artificial intelligence is this concept of machine learning, where we basically can train a machine to look at a data set and make some kind of prediction from that data set, right? And what it's ultimately doing is trying to emulate human intelligence, because we process data, use that to come up with some kind of prediction or conclusion from that. So artificial intelligence is an umbrella term for machines capable of perception, logic, and learning. A subset of that is machine learning. So machine learning employs algorithms that learn from data to make predictions or decisions, and whose performance improves when exposed to more data over time. And then an even deeper subset of that is called deep learning, which are really, really advanced machine learning models that are capable of higher level, basically, emulation of human intelligence. So when we think about artificial intelligence, we have to kind of think that about what is actually intelligence versus artificial intelligence. So intelligence, human intelligence, is the ability to use logic and problem solving to adapt. In a kind of simple definition, we often associate intelligence with perception, learning, memory, reasoning, and problem solving. Artificial intelligence refers to computer systems or machines that can perform tasks that mimic human intelligence. We often associate artificial intelligence with visual perception, speech recognition, natural language processing, and decision making. So you'll notice for both of these terms, intelligence and artificial intelligence, I've got this list of things we associate with them, but there is actually not a single universal definition for either of these terms. If you were to ask a biologist what represents intelligence versus a computer scientist versus a psychologist, you're going to get very different answers. So intelligence is not one thing. We can think about intelligence in a variety of ways, right? You could think of emotional intelligence. You can think of your ability to use logic and reasoning, your memory and recall. There's lots of different ways that we can think about intelligence. And similarly, when we think about artificial intelligence, it's just as diverse because we're just mimicking that. So now that we've got that covered, how do you think we could potentially leverage artificial intelligence in the field of paleontology? What are some uses either you've heard of or you could just imagine you might be able to apply? Yes, sir.
Using a phone or something, the camera, just to point at some object and find out what.
So some kind of identification from like an image or video, right? So that's that visual perception that we mentioned as one of the ways. Any other ideas? We talked about processing large data sets. What are some examples of large data sets that might exist in paleontology?
We got lots of structures.
Sure.
How do you extrapolate from that to the different sharks, the different lineages, the different sizes, the different feeding habits, the different.
Yeah, so maybe something in that vein of we've just got this massive database of information about fossils and we want to process it in some way. So a very common example, how many of you are familiar with what a phylogeny is? Heard this phrase. Phylogeny is basically an evolutionary tree, right? It's like a tree of life. That involves processing large amounts of data where you're marking these different characters, these different traits on fossils. So a lot of programs, when you develop those trees, actually underneath the hood, you don't realize it, but they're utilizing machine learning. So AI is already being used by paleontologists, even when they don't really realize they're using it in many cases. And I'm sure if we spent more time, we could probably brainstorm some other ways we could leverage this technology. But the main one, the first example you mentioned, which is visual perception, or in the field of AI, often referred to as computer vision. So this is the field of AI that enables computers to derive meaningful information from images, videos, or other visual inputs, right? So again, let's think about how this operates for a human. We've got some object in front of us that we get a visual image of. Our eye acts as a sensing device. That sensory device then passes that information onto our brain, which processes that to classify this in some way, right? And we can classify it in a bunch of different ways. There's not one answer for what this is. There's a lot of different answers for that. So the way a machine learning model works is the input is that image or video, some visual input. A camera might act as the sensory device, like our eye, and then the computer itself is acting as our brain, processing that information to ultimately come up with some prediction. But that prediction is going to be limited based on whatever categories you define when you categorize that data, when you train your model. So am I classifying this by color? So there's different categories, and the output is then going to tell me it's orange. Am I classifying this by a collection of different objects, and it's ultimately going to tell me it's a bottle? Am I classifying this by different brands, and it's ultimately going to tell me it's Gatorade, right? So any data set can be subdivided in an infinite number of ways. We as humans constantly are creating different classification schemes to interpret and understand and communicate information. Everything you know or think you know is built around some classification scheme. The most complex and important one that we use is language, right? Think about how diverse language is as a classification scheme. So now you want to train a machine to be able to understand that language. That's a pretty challenging task, but that is what we're now doing, right? When you interact with things like ChatGPT, it's natural language processing, a form of AI. But for this project, we are focusing on this particular branch, computer vision. So our project over 3 years, we had basically 3 different cohorts of teachers where we led this professional development workshop at University of Florida. We had these teachers act as students and learn this curriculum that we were then asking them to implement in the classroom. So it's a week-long professional development workshop. They get comfortable with these different lessons. Then over the course of a school year, they're implementing those lessons and gathering data that we're reporting back to the National Science Foundation, doing our research. In addition to all of those teachers, we had a lot of different STEM professionals, including faculty, staff, and students, a couple of which are in this room, that helped us with this project. So ultimately, this is kind of what I'm describing is what we call this teacher professional development cycle. So in the summer, we host this week-long professional development workshop at the Florida Museum of Natural History in Gainesville. Teachers learn and get confident with the content they're going to have to teaching in the classroom. Over the course of the school year, teachers are implementing this curriculum at their own pace, which is critical. When you're working with teachers, you should not be prescribing anything and say, this is how you have to do it. Because every classroom is different. So teachers need to have some flexibility to be able to modify these lessons to fit within their curriculum. So that was a really critical thing. It can't be, I've got these 5 lessons and you need to teach them back to back to back. They had to figure out how to fit these 5 lessons into their existing curriculum in a way that it didn't feel like they were adding on to what they already had to teach. The curriculum is not trying to be additional things that the teachers have to teach. It's a new way to teach standards they're already trying to teach to their students, right? So that's another thing. Whenever you're trying to work with teachers, understand that they're already stretched entirely too thin. You can't add on to it. You have to kind of supplement what they're already doing. During that year-long implementation, we also had these quarterly check-ins with the teachers to see how things were going, if there are any issues they were running into with the technology or whatever they might have, right? An opportunity for them to communicate with us, progress, ask questions, tell us about problems. And finally, during that school year, each teacher was also required to request a scientist role model visit. So one of the programs we partnered with is called SEFS, Scientists in Every Florida School. And they basically act like matchmakers between teacher and scientist. So every teacher was required to bring in a scientist that could hopefully help them teach one of these lessons. But if they so desired, it could actually relate to something entirely outside of our curriculum. They just had to have that scientist role model as a part of this program. Finally, the following summer in June, we would have a one-day wrap-up session where teachers would kind of present their experience implementing these lessons. And we'd get kind of a debrief and get a lot of our evaluation data about the effectiveness of our program. Now, teachers were able to continue to remain involved by either returning the following year as a teacher leader. So when we get our second cohort, we have teachers that have already gone through this program and kind of help these new teachers get used to the process. You know, why not involve people that are already familiar with this, that are already working with similar students and maybe even in the same schools. The other option was that teachers could return as a participant again. Some teachers just, even though the professional development didn't really change from one year to the next significantly, they just wanted that additional kind of time to relearn and refamiliarize themselves with that curriculum. So this was the process of this grant that we did over 3 years, which actually just ended in October. So this project is now complete. So here's our curriculum. Our curriculum is separated into these 5 modules. Again, they could be taught in a sequence over the course of a week, or they could be spread out across an entire school year. It's entirely up to the teacher how they did this. The idea of these modules is a learning technique called scaffolded learning, which basically means in module 1, you're going to learn things that help you in module 2, that help you in module 3, that help you, and so on, right? And this is something that pretty much any teacher is familiar with and utilizes. It doesn't really make sense to just jump into how do you create a model without first having a conversation about what is artificial intelligence, right? So our first module, Introduction to Artificial Intelligence. Our second module, Shark Tooth Classification and Data Collection. Those are basically foundations that the students need before they start to develop a model. Module 3, Training and Evaluating Machine Learning Models. Module 4, identifying biases and limitations in machine learning data sets. So you've built a model, now how do you make that model even better? And then finally, Module 5, conceive your own machine learning model. Now that we've taught you this process for identifying shark teeth, how could you replicate this process to identify anything that interests you? That is the sequence here. So what I'm going to do is I'm going to take you through each of these modules, tell you a little bit about what they entail, and show you some of the outcomes in the classroom. So these pictures are during our professional development workshop. So these are the teachers acting as students going through the modules, right? You can see somewhat up there, there is a slide with different pictures. And what it basically asks is which of these things has intelligence, right? So there's objects like animals and plants, but also a smart TV, a smartphone. Just because it has smart in the name, does that mean it has intelligence? Trying to get some of these maybe tricky things for students to really define what is intelligence. What you see in this bottom picture here is a teacher leader, so someone who had participated in the professional development and now is returning back and sharing their experience of implementing this curriculum with these new teachers. So in this first module, our driving question is, how is artificial intelligence used in our daily lives? And our primary learning objectives is explain the difference between intelligence and artificial intelligence, which we just did collectively, right, a couple slides ago. Identify common examples of artificial intelligence applications. So where are you actually using this already? And describe how artificial intelligence can be used in citizen science. So, okay, how could we actually use artificial intelligence to benefit science? So now here are some pictures from the students doing this, the middle school students. So a lot of activities that teachers would use would be draw a picture of artificial intelligence or write a few words that you associate with artificial intelligence. This is how we're capturing their conceptions and misconceptions of what artificial intelligence actually is. We also encourage teachers to utilize existing phone apps like iNaturalist and Seek, which basically use computer vision to identify living organisms today, which is exactly what we want them to do with fossil sharks. So some of the quotes that exemplify the outcomes here. The kids started off with the free association drawing activity where I said the words artificial intelligence and then let them draw what came to mind. I learned that a lot of them think that AI involves scary world-conquering robots, right? Common misconception when you hear artificial intelligence is Terminator. And while we already kind of know that, this validated that. And again, you can kind of see it in some of the drawings from the students. Another one here In using Seek and iNaturalist, the students were able to explore and evaluate the possibilities and limitations of AI machine learning by comparing how well the apps identified known plants. So now they're starting to, one, recognize how they might already be interacting with it, because not only can you do this with iNaturalist and Seek, but most smartphones now, it's already embedded into your camera. So this computer vision, you don't even need to open an app necessarily, like it's already built into your phone. And they can start to think about how this might apply to science. How can we use this for science? And finally, students were very surprised how much AI is already in their daily lives. They're starting to appreciate that I'm already interacting with this frequently. So that's a good reason for me to want to understand it. Our second module, shark tooth classification and data collection. Our driving question, how do scientists use qualitative and quantitative data to classify objects? So we, in this activity, basically create these shark tooth kits and have students sort them out without any context. So we're not telling you to sort them by species. We're not telling you to sort them by function or shape or anything like that. We're just saying, here's some teeth. If you are a paleontologist, you just discovered these. How are you going to organize them and make them explain the categories that they create? So some might do it by color. Some might do it by size, by shape. In Florida, inevitably, some student actually knows the species and does sort them by species. But ultimately, we're just thinking about what does it mean to create a classification scheme and how do you justify it and what can you learn from it? So the learning objectives, explain strategies for classifying shark teeth using both qualitative and quantitative data. We're specifically emphasizing qualitative and quantitative because that ties into the learning standards that teachers are already required to teach, right? Again, not adding on, just supplementing a new activity to teach the same standards. Understand how paleontologists classify fossils. So once they've completed that sorting activity, we then give them this identification guide and ask them to resort those fossils into the different taxonomic groups. Again, Linnaean taxonomy, required learning standard for middle school students. And then our next one, relate tooth shape to specific functions and diet. In the middle school curriculum, in terms of their standards, this is referred to as structure and function. In paleontology, we often call this functional morphology. So how does tooth shape relate to a specific function, whether it's grasping, cutting, crushing, and how does that then correspond to a diet? So they're learning about adaptations now through this activity. And then finally, describe the importance of databases for organizing, storing, and managing data. These are required learning standards in the computer science curriculum. So again, we're hitting a lot of different required standards, expectations for teachers already, just a new way to kind of engage with them. So this was definitely one of the most popular of the modules because students got to work with real fossils during this, this portion of the curriculum. We look at some of our quotes here. The project increased student learning by establishing connections to real-world objects. Nature of science standards were addressed via classifying, collecting quantitative and qualitative data. Sixth graders love learning how to use a caliper, how to record data, and what the functions of the different teeth were. The interest in shark teeth fossils coincided with Miss Vallejo Perez and the students' interest and questions, some of the best in-depth knowledge gains I have witnessed in teaching. So this is that scientist role model visit. So not only is doing those modules significant, but having that career role model in the classroom just made it all that much more real, right? You're not just working with real fossils, you're working with real paleontologists while you're doing this, if a teacher elected to bring in that role model visit for this module. So in a couple of these pictures, you can see Dr. Bruce McFadden, who was my PhD advisor and one of the other PIs on this grant, and a PhD student who worked on this grant doing some of these classroom visits. Our next module, training and evaluating machine learning models. Our driving question, can we create a model to identify fossil shark teeth? Now we're getting into the meat of the curriculum. We're going to try to build something that can identify a fossil. Our primary learning objectives, we want to understand the input and output data in machine learning models. We want to recognize the data organization is determined by the research question being asked, right? Are we using that Linnaean taxonomy? Those are going to be our categories. Or are we using that functional structure and function classification scheme? Depending which one you're using, you're going to have different input data for your model. And they're going to ultimately, that output, the prediction, is going to answer a different research question. We wanted them to really appreciate that. And again, it's building off of that module 2 when they sort it into different ways. Now thinking about what can we actually answer with these classification schemes. Finally, interpret the model output data, the model predictions, and evaluate the classification accuracy. Okay, you created a model, but is it actually identifying that tooth the way you wanted to identify that tooth or not? Is it working? So again, you see the teachers acting as the students, working through this process of developing these models. You'll see a couple of people over here in this photo. These are, again, returning teachers and teacher leaders, helping the subsequent teachers in the other cohorts learn. So before I show you the classroom outcomes, these are the platforms you're using to build these machine learning models. And they're both free. So if you yourself wanted to learn how to create a computer vision model, any of you could do this. And I promise you, it is not that difficult. I had a bunch of middle school students doing it, so I'm confident every single one of you could as well. So the first one is called Google's Teaching Machine. This platform only allows you to create a single type of machine learning model called single label classification, which basically means that the photo I use in my training data cannot have multiple objects in it. So I can't submit a photo that has a bunch of different shark teeth in it because the model can only make one prediction. So it can only have one object in that image. Make sense? Because if I had a bunch of training data with multiple teeth in it, the model is going to be completely confused about what it's looking at. So it's a very basic form of machine learning model when you're doing single label classification. Great thing about this platform is it's through a web browser, so you don't have to like download an app or anything. You just go to the website. It doesn't require any form of login. So think again about our audience, middle school students, privacy issues. If we had to create logins, I would create barriers for our teachers to implement. It was extremely easy to use. So Google's Teaching Machine was created in 2017. And when we submitted that grant, we were asked to look into other platforms that might be used because everyone was basically using Google's Teaching Machine. It was the most dominant kind of open source platform that people could use. Quick on-device training. So when you upload all your data into that model, ultimately click this button, train, it's happening on your computer and it happens within a matter of minutes. So it's pretty fast. You get kind of an instant gratification from the work you did of developing your model. And it offers some very simple evaluation tools. So this picture up here is called a confusion matrix. One axis is basically your classes, what you labeled it as. And on the other axis is the model's prediction. So when you see a 15 in that corner in blue, those numbers are the accurate identifications. Any number that's not in that darker shaded blue is a misidentification. So you can see in that particular example, there's only 2 misidentified teeth. The model was doing pretty well, but it was confusing. Looks like tiger shark Galliacerdo with a carcharinus tooth in one example, and it was confusing a megalodon tooth with a carcharinus tooth. And knowing what the images look like, I can kind of predict why that was happening. For example, megalodon tooth, if you get some of the posterior teeth that are smaller, they can have a lot of overlap with particularly bull sharks because bull shark teeth can have a burlette similar to megalodon. So I can now look at that and say, I need more training data for those classes in order to correct for that bias in this model. So Google's Teaching Machine became our main platform, but since National Science Foundation wanted us to look into another platform, I tried to do some research about other platforms where we could develop these machine learning models. And one I came across is RoboFlow. It is also free, but it is a more complex tool. It offers more variety in what you can develop. So you can do the single label classification, but I can also do object detection and instance segmentation. These are 3 different types of models. So in object detection, think about the way that if you're driving a car, maybe like a Tesla has these, it's identifying objects in the road to make decisions about how the car operates. So in that case, there is not one object that model is focusing on. It's focusing on a whole bunch of different things in that image. So with object detection, let's say I go out and collect for a day and I put out all my fossils on a little paper plate to dry. I could take a picture of that plate and label each tooth in that image and use that as training data. So I can have multiple objects in that same image, or a single label classification, one object per image. Instance segmentation is even more complex if I want to identify components of something. Let's say I want to distinguish between the root and the crown of a tooth. I can actually isolate those two things in an instance segmentation model. So we're basically getting increasingly more complex in the type of function we're asking this model to work with. So I can do more things, which is kind of cool. It makes it a little bit more real world with RoboFlow. It is free, but it does require a login. So remember, privacy issues with students, this was a big barrier. It basically kind of ruled out RoboFlow as a viable option for most of our middle schools. It does offer this optional paid subscription, which will give you access to even more advanced features, but that is more so for people that want to produce a product that they're going to commercially sell rather than just students trying to learn. So if you're just using this platform to kind of play around and learn how to develop a computer vision model, you can use it for free. It offers what's called data augmentation tools. So let's say I've got an image of shark teeth, and every single picture of the shark tooth has the root at the top of the image and the crown pointing down. Now, all of a sudden, I want to figure out what this tooth is, but the input image I submit is flipped. The root is at the bottom and the crown is pointing up. That creates what we call an orientation bias. The model has only been trained to look at the image in one way and is not used to now this new input you're trying to ask it to process. Data augmentation is a way to take your training data set and basically provide some kind of manipulation to it. So I'm not taking more pictures, I'm just manipulating my existing pictures. So I've got my original image. I can rotate it 90 degrees. I can rotate it 180 degrees. I can rotate it 270 degrees. Now I've got the same tooth, but it's represented in 4 different orientations. I'm helping the model account for that variation in how the tooth might be positioned. So you can do a whole bunch of different manipulations to your training data set. And ultimately, you're increasing your data set. So it's training the model to learn better what are the actual important features for identifying that tooth. And it does it in a really quick way where I'm not just taking thousands and thousands of pictures to account for all that variability. So that's a really cool feature in RoboFlow. It is also a social media platform. So other users, you can see the models that they're creating. I can even download other people's models and build on top of it. So one thing that happened in the process of this grant is we were creating some models, testing this, and some researchers downloaded our model and then added additional classes to it and published on it before we were able to finish our paper on the project, which is both good and bad, right? It meant that what we were creating could be leveraged for others to advance the field, but it also meant that, they beat us to the punch in terms of getting that published and getting kind of that press attention that comes along with it. In my mind, I was just happy to see that what we used led to something even more advanced. So RoboFlow was great. It was very useful, but not for our middle school audience. One thing that happened when I went to St. Mary's is I ultimately ended up teaching a course on AI and natural history, where I basically took this curriculum and expanded it for an undergraduate audience. And for my undergraduate students, RoboFlow is by far the better tool over Google's Teachable Machine. So thinking about who your audience is makes a big difference about which platform is kind of the appropriate way to get into this. So again, if any of you are interested in creating some kind of computer vision model to identify things, I would strongly encourage you to play around in Google's Teachable Machine first, just to kind of understand the process, and maybe step into RoboFlow if you actually get used to it and want to develop something more usable, like a true end product. And again, this process is super simple. So when you look in this picture up here, you see these different categories. Basically, the process of creating this model, the input data, is I label it. So let's say Carcharinus. I upload images, and then I create a second category, let's say Megalodon, and I upload images. And I do that for however many categories I want to be in my model. Once I've done that, I hit this button that says train, and it automatically trains the model on the data I've implemented. And then again, in a matter of minutes, I can start testing that model to see how well it's working. So it is a very quick process. The most time-consuming part is getting the images, the actual training data that you need. And that's where Stephen and Mason were helping us out aggregating data used in these models. So yeah, I definitely encourage you all to check that out.
Quick question.
Please, yeah.
So, I mean, with any shark tooth, like the Odontocus that you showed,
Mhm.
mouth position is going to have such a dramatic effect on the
Identification.
picture. The
Yeah.
ID. Which program better does that?
I would say
even just like this one, they're pointing left, the other one they're pointing right. You know.
yeah.
But we wanted to call it the same name.
So technically, RoboFlow it uses an underlying model that's more advanced than the underlying model from Google's teacher machine, if that makes sense, right? So the model for Google's teacher machine is called MobileNet. It was specifically designed to be able to process data sets on devices like a laptop or even a cell phone. The model that's being used in RoboFlow keeps being updated with basically the most advanced model that's out there, and it can't process it on your computer. You have to hit train, and then it actually they train it on their servers, and then it's basically uploaded onto the site. So you don't get that same instant gratification that you get from Google's teacher machine, but the end product is a more robust model. That makes sense. But really what you're asking when you say which model accounts for tooth positions better, ultimately it really just matters how good your training data set is. So did you upload enough images to account for that variability in tooth position? So two ways to do that. Take more and more pictures of teeth to account for that variability, or apply those data augmentation tools. So let's say, again, one form of bias could be left versus right. One tooth's angled this way, one tooth's angled this way. The model doesn't know that it's just left versus right as a difference. It sees it as two different things. But I can mirror that image, and now I've got two pictures representing that tooth, one angled to the left and one angled to the right. I've doubled my data set, and I've accounted for that bias. Instead of taking twice as many photos, I just clicked a button in the program to do that basically automatically for me. So you can do that in RoboFlow, can't do it in Google's teacher machine. But that gets into our next module, which is identifying biases and limitations in these machine learning data sets. So basically, we want them to start to figure out, is there a left versus right bias? Is there some kind of orientation bias? Is there variability in the background color of the image? What is the extraneous data, all the data that exists in that image that isn't the tooth, that could be making the model not perform the way we want it to perform? So what you're seeing in this picture here, you've got one teacher holding up a 3D printed megalodon tooth, and she's using the webcam. They're using the webcam on their computer. So what does that mean the background of that image is? It's herself, right? It's her. It's a complex background with a bunch of different things that could distract the model from focusing on the tooth. What you see in this next picture is a teacher holding a piece of white paper behind it. They're simplifying the background to see if that affects the identification the model has. Then you see another teacher here using the back of their computer to create a black background. So if the training data, the images they uploaded, all had a black background on it, then your model might get really confused all of a sudden when you ask it to identify a tooth and the background is not a black background, because you've added a new variable that it has never experienced in its training data set before. So this module is all about basically trying to figure out, when does your model not work, and kind of come up with a reasoning for why it's not working. And in many cases, because we provided the images, we know that there is a bias based on background color and based on orientation of the teeth. So the convention for photographing shark teeth is, if it's a lower tooth, the crown points up. If it's an upper tooth, the crown points down, right? So there's a tooth positional bias when you're taking images from a museum's collection, because they're reflecting what tooth position you're looking at, up or down. So unless you rotate those images so they're all in the same orientation, you have an orientation bias in your model. So yeah, they are in this question. Driving question for this module, how can we improve our model's performance? We're trying to identify the bias in the model input data. We want to interpret the internal evaluation metrics provided by Google's teacher machine that confusion matrix I showed you before. We want to recognize model limitations by testing performance on things like incomplete teeth. All right, so your model's doing really great, but you provided it with a ton of pristine teeth. How realistic is that in the actual fossil record? Can your model identify a broken tooth? If you don't have training data that represents broken teeth, the answer is probably no. Discuss human biases in the development of machine learning models. So if this exists in a model to identify shark teeth, what about models that are identifying people? How does race and gender and those types of variables impact model performance? So for the teachers willing to address it, which is not all of them in the state of Florida because it is a little bit risky to talk about some of these things, they can actually address some of these larger social issues that exist within AI using shark teeth as kind of the simple entry point to have that conversation. So here's modules 3 and 4 in the classroom. So now we've got the students playing around. You can see they're kind of trying to hold that tooth up in front of the webcam. So they're taking the teeth from their shark tooth fossil kits from module 2 and testing the models that they built to see if they can accurately identify those teeth, playing around with different variables, whether it's rotating the tooth, changing the background, trying to see what makes the model work and when it doesn't work. So some of our teacher quotes from this module, or these 2 modules: I appreciated that it was challenging and frustrating at times. It allowed the students to collaborate to solve their problems, right? You don't want it to just be a straightforward, easy answer. Like if it was that easy and there was no complication, it wouldn't really stick with you. You wouldn't feel accomplished at the end with what you created. You have to struggle a little bit to really appreciate the end outcome. Students struggled using the computer cameras on Teachable Machine and positioning for the shark teeth. However, this struggle allowed them to better understand limitations and biases when using a machine learning model. So yeah, you're holding that tooth and your identification keeps switching between Megalodon and Carcharodontis, and you're annoyed because you want it to work correctly. But you're starting to realize that just by a slight variation of how the tooth is rotated, the model's not working. So you start to appreciate that it isn't perfect and it can be improved upon. Students also became very competent at storing and using folders in their accounts, which is not a skill many of them had before this module. This was an unexpected outcome. We didn't think about the challenges of just downloading images, sorting them into folders on a computer, right? PhD level academic, I'm messing around with files all the time, downloading things, organizing it on my computer. It can be easy to forget the level of competency that a middle schooler might have doing some of these tasks. So this is one of the moments where we kind of had to step back and realize that we needed to offer more training just on processing and organizing data before we could get into some of these deeper level conversations. All right, module 5, conceive your own machine learning model. So what kind of machine learning model do you want to create? We've now taught you this process. Label your different categories, upload the images, train your model, evaluate the model predictions, go back and now try to improve your training data set to make your model better. Okay, we did it with shark teeth. What are the different things that you want to try to identify now? So we want students to demonstrate understanding of the machine learning development process. Doesn't matter what the object is you're classifying, the process is the same. Outline the structure of a unique machine learning model. What are the different categories? How much data do you need to upload? What kind of variables are you going to account for that might bias your model? Recognize the wide variety of potential machine learning models that could be created. Again, think about what already exists out there like iNaturalist and Seek, and then think about how much more broad that could get once we develop these really robust training data sets. So again, we've got our teachers doing that here, struggling through it. And I'll tell you, they do struggle through it. Like during some of these professional development workshops, teachers were in tears because they were struggling to figure out the technology. But how important is that a reminder for them what their students are going to feel when they have to encounter this? So easy to forget, again, what it was like when you were a middle school student. All this information is new to them the same way it was new to them when they're doing this professional development workshop, right? So yes, it was difficult, but ultimately at the end of the 5-day, week-long professional development, it was all smiles and happiness. But days 3 and 4, when we're teaching about module 3 and 4 in particular, they struggled as well, the same way that their students were. And that was important, I think, for them as well. So here are some of the models that students created in the classroom. So it wasn't actually required of them to create their model in Google's teacher machine. They just had to define like the outline, the structure of the model. But some teachers took it further and actually allowed their students to develop the models that they had envisioned. So we get a mix, as you can see in this second quote here. The last lesson where we had students create their own model in Teachable Machine was a mix of kids who really liked it and kids who were just silly. So I've got models on cloud identification, where they're uploading different pictures of clouds and labeling the different categories. Got a model on neurological disorders, where they found images of brain scans and classified those. And then you've got models like Harry Potter houses, classifying the different houses in Harry Potter, and shoe brands, so Nike, Adidas, whatever. The student literally took the shoes of all of their classmates and took pictures of them and then uploaded them into Google's Teachable Machine to train a model, right? So many of them are able to replicate this process, but not all of them are necessarily producing a model that had necessarily a meaningful or maybe marketable use. But either way, they're demonstrating that they understood that the process they learned could be applied to anything you want to classify. So the other quote we got on here, students became very creative in their categorization arguments and models, right? So I'm showing you 4 examples, but we had hundreds of students creating these different models. So we got a whole wide range of different outcomes in this last module. So to summarize some of the major project outcomes, the professional development and curriculum help participants identify and correct misconceptions about artificial intelligence and increased awareness of the ubiquity of artificial intelligence in their lives. And this is true for the teachers and the students. We saw that those misconceptions weren't just middle school students, it's also teachers that have them as well. And through that first module in particular, they were really starting to understand what is an accurate conception, what's a misconception, and how common AI is already in their lives. Authentic fossils and sharks increase student engagement and interest in learning about AI and machine learning, right? We didn't have to do this lesson with fossil shark teeth, but it made it a lot more fun for the kids to be able to do it with shark teeth than some other random object. So again, it's not so much the importance of teaching paleontology, but using paleontology as a tool to teach other things. Many teachers and students struggled with using the technology, but this ultimately led to an increased appreciation and understanding of AI. That struggle was a necessary thing to get the outcomes that we wanted. We don't want it to just be, you got the right answer and it's done. We want you to work through it. We want it to feel real world. We want this to be authentic. Students expressed increased interest in STEM plus C careers, STEM being science, technology, engineering, mathematics, C being computer science. And highly valued the scientist role model visits. Having that authentic scientist in the classroom, again, made it more real, made them appreciate it, and made them start to think about careers they might not have been considering prior to interacting with the modules and with these folks. This little table I have up here, this is the ratings we got on a 5-point scale from our 3rd cohort of teachers. So the last round of implementing our professional development workshop, 5 being the highest score, meaning it was great, 1 being the lowest score. And you can see for each of the modules, we are above 4.5. So overwhelmingly, the teachers loved this curriculum. And you can see that module 2, when they got to interact with the real shark teeth, was a peak. And module 4, when they got to learn about biases and limitations, those 2 modules were the favorite amongst our teachers. And one more quote from one of our cohort 2 teachers: Seth, scientist in every Florida school, was absolutely a game changer for my students exploring careers in science. So again, just emphasizing the significance of having that scientist role model visit as a part of this curriculum to really emphasize the diversity of careers and the potential pathways and all these different things that kids could learn about. Again, if I had this type of experience when I was a kid, maybe I wouldn't have tried to go for alternative energy as my first career path. Maybe paleontology would have been my immediate choice. But the fact is, I knew paleontology as a collector. I didn't know about it as a profession. I had to learn that basically while I was a student, an undergraduate student. So we do have a project website. I've got the website listed there. I also have a QR code if you want to scan it with your phone. So our entire curriculum, all of the lessons are on here for free for any teacher in the world to download, or any person, don't have to be a teacher. Anybody in the world can download and use these. There is a PowerPoint presentation that goes with each module to help People follow the steps of what we expect them to do. So if you want to play around with Google's Teachable Machine, RoboFlow, all that stuff is linked within the curriculum here. So we'd love to hear about the different types of models you all try to create if you so desire to experiment with this. And again, I want to emphasize that this is not me working alone. I worked with a lot of different people. So there was 4 principal investigators on this project, myself, and then 3 faculty at University of Florida. We had Dr. Bruce McFadden, paleontologist, Dr. Pasha Antonenko as a professor of educational technology, and Dr. Jeremy Waysome, professor of engineering, specifically focused on engineering education. And then we had a ton of other people. We had support staff from the Florida Museum of Natural History and University of Florida. We had an external evaluator, which is often a requirement for a National Science Foundation grant, to have some outside source evaluate your project. We had project coordinators, and we had a number of graduate and undergraduate students, again, highlighting a couple in the room, that helped us out with this project. This was not something I did alone. This is something that a whole village worked on to try to create a really, really robust curriculum that teachers could use. I believe, yeah, that's my last slide before I get into the PGPaleo program. So I think I'll pause there for a moment to just see if anyone wants to ask me questions about Shark AI. Anything about Shark AI that interests you would like to talk about?
So if I understood correctly, 5 days was with your teachers.
Yes.
What about with the kids?
So again,
they have 5 days to develop.
It was up to the teacher to decide the pacing. So some teachers, they implemented it in a week, did all 5 lessons day after day after day. Not most. Most teachers spread it out over their curriculum and kind of fit the lessons in where it made sense with their existing curriculum. Some teachers even swapped modules 1 and 2 because they wanted to talk about Linnaean taxonomy earlier in the school year and didn't want to get into AI immediately. So again, when you're working with teachers, you have to be flexible with them, allow them to implement it in a way that works for them. So yeah, some a week, some a whole school year.
Do you mind going back 1 slide so I can see the address?
Of course. No problem.
How many images did you start out with for like the data packets that you gave students for uploading to train the program?
Yeah.
Because it sounds like some of the kids were starting with like a small database for the programs they were making.
It's a great question.
How many was it that you were using for the bigger data set?
So what we did is Stephen took a bunch of photographs of fossils at Calvert Marine Museum. We had a bunch of photos of fossil shark teeth from the Florida Museum of Natural History. And then we also got a bunch of shark teeth off of my fossil, which Mason aggregated, I believe, most of those. So we had a Google Drive folder that had the Calvert Marine Museum as a set of photos they could download, the Florida Museum of Natural History as a set of photos they could download, and then my fossil, this avocational paleontology social media platform. So there wasn't like a fixed number of images that students had to download. They were basically able to pull whatever data they wanted from those, and that created variability in the data sets. So we could figure out, if you're pulling exclusively from Calvert Marine Museum, you're going to see a lot of consistency in those images because they were all photographed in the same place using the same camera system with the same scale bar. Versus if you take it off of something like my fossil, where it could be uploaded from anybody in the world, there's a ton more variability in those images, a lot more variability in the quality of the images, the color of the backgrounds, the orientation of the teeth, inclusion of a scale bar or not. So depending on the source of your data, it could introduce different variables to your data set. So we could have created a super clean data set that produced a perfect model from the beginning, but then they wouldn't have struggled to produce a perfect model, right? Yeah. We intentionally made it a little bit more challenging to make it somewhat more real world. Like if any of us wanted to create a model to identify fossils from Calvert Cliffs, there's a lot of different places we could get those pictures, whether we take them ourselves or start to just scour the internet and download them. We did do a separate research project, kind of almost a parallel to this. We also wanted to figure out how effective could this be for future paleontological research. It was not a priority for the grant, right? Because this was that iTest program, which focuses on education, but we're scientists and we want to figure out, how might we leverage this in the future for ourselves. So we did do a separate project where we basically produced models in with sample sizes of 50 increments. So we had 6 different species of sharks, trained a model with 50 images for each of those species, then trained another model with 100 images per species, and went all the way up in 50 image increments up to 500, and tried to figure out what was the threshold where the model basically plateaus, and it doesn't matter if you add more images, it's kind of already functioning at peak performance. For those 6 species that we chose, it was about 150 images where we hit that plateau. But again, if you think about it in a real world scenario, like I want to apply this to Calvert Cliffs, is it really useful to have a model that can only distinguish between 6 different species? No, there's 54 different species of sharks and rays known from Calvert Cliffs. We'd have to create a much more complex model to really figure out how it works in the real world. But the application of computer vision for the field of paleontology is still pretty new. And we kind of wanted some baseline data to start to kind of lead people in the direction of a more realistic model. So that paper has been submitted. It's already accepted. It'll be published in the journal Paleobiology. So it's in press right now. Will come out soon. If it was already released, I would have, advertised it to you all today, but it hasn't come out quite yet. Thank you.
There's a question on Zoom.
Sure.
There's a question. I was going to ask for unmute. I'm not sure how to. Yeah, see if you can find out the question.
Maybe type in the chat. Any other questions from our in-person audience while we're waiting on that? Out of curiosity, any think you're gonna attempt to go onto Google's teaching machine? Feeling curious? Maybe.
Yeah, I like looking for rattlesnakes out in Arizona.
Mhm.
So I was thinking that it'd be cool to put a camera on the front, with hooked up to a computer, and as you're going down the road, train it to know snakes from sticks, from
Yeah.
hoses and things like that.
So
I noticed when we're finding a lot of snakes, we almost always find snakes, but then when we're not finding them, we're stopping from every little thing.
yeah.
But if you had some AI that could tell you what it is.
Yeah. So for my undergraduate class, all my students had to produce their own model, like that kind of our 5th module, conceive your own model. And I had 2 different students that actually did snake classification.
Okay.
They work decently well, but the challenge is that snakes can be in so many different orientations that you would need a very large data set, I guess, to really account for that level of variability.
Yeah.
We talked about some potential solutions, like quite a few snakes are identifiable from the head alone. So you could simplify the task by just using images of the head and not focus on the overwhelming complexity of the body, but then you're limited to which snakes are actually identifiable from a head alone. You could have specifications that the snake has to either be coiled or it has to be completely elongate. So there's one orientation you're accounting for. So there's ways to, I guess, reduce the variability, but it basically means that when you want to use that model, you have to mimic whatever your training data set looks like, right? You can't expect your model to all of a sudden be able to deal with a complete snake if you only trained it to identify snake heads. Mm-hmm. But if you go to RoboFlow, because it's that social media platform, you can find my students' models on there and see what they produced. And if it did seem like something you wanted to build off of, you could even download it, add additional categories, add more images to it, and not start from scratch, right? So that's the really cool thing about RoboFlow. It is this community of people that are just interested in developing computer vision models. And every single model that, if you're using the site for free, one of the agreements is that your model is publicly available for anybody. So that's why other researchers were able to download our model and build upon it, because we were using it for free. So it was publicly available for anybody.
When they built upon it, what were they using it for?
Also, shark tooth identification. They just added different species to it. And they didn't use RoboFlow. They downloaded the data set, but they coded their own machine learning model, but just built upon our training data set. Remember, the most complicated, time-consuming part of this is aggregating all the images. So we did a lot of the heavy lifting for them, and then they were able to just kind of process that data and add a few more species to it. Were you able to get their question?
Okay, so she's asking specifically about Cambrian work. She's interested in doing this on Tully monster.
Yeah, I mean, it can be applied to anything. You just have to have enough images, right? And what exactly are you trying to distinguish? What are the categories? Are you identifying different species? Are you trying to identify Tully monster versus a rock that isn't a fossil, right? You have to decide what are the different categories, what are the options that my model is going to be able to choose from, and then you need to have sufficient images for those different categories. So this is where it gets challenging, right? Like if I wanted to create a model that could identify any fossil from Calvert Cliffs, which doesn't sound that crazy, but when you start to think about it, it would be an insanely difficult challenge because a fossil can break in an infinite number of ways. And with fossils, you know, you also have so many different elements from the body. So if I wanted to identify every type of fossil, I would need a category for maybe teeth, category for a specific limb bone, category for a vertebra. They can't all be lumped together. You have to split them up because the model has to be able to distinguish those things. So it's more realistic to create small models that focus on more specific tasks, like just identifying a shark tooth, right? Not every single fossil in the world. So I would encourage them to think about what are the different categories that you're trying to distinguish between, and then think about where the data is actually going to come from to produce that model.
Another question in the chat: do either of the platforms identify species not in the training set as not a good match to its categories?
In RoboFlow, there's an option to create what's called a null class, which basically means that in a given image, there is no representation of the different categories that I included. The way that you train that, so let's say we're doing snake identification. I would have to upload some images of pictures that do not have any snakes in them and label it as a null class. So the model starts to recognize when there is not a snake in the picture. But again, that gets really complicated because not a snake is a lot of different things, right? I could take a picture of myself and put it in the not a snake category. I could take a picture of the screen behind me and put it in the not a snake category. So that null class can get really overwhelming really quick. And that's, again, why it comes back to just reducing that task to something more specific that's more manageable. The more complex you get, the more categories you get, the less likely your model is going to perform properly. But our data sets are always growing and we're getting closer and closer to something.
And do the models give you a confidence level?
Yes, they do.
Okay.
And in RoboFlow, you can actually set a confidence threshold. So if it is, let's say, if the model isn't at least 75% confident in its prediction, I'm going to consider that a false identification. So you can change what that threshold is, what you consider acceptable. I think it defaults like 50%. Like as long as it's above 50% confident, it considers that inaccurate, but you can change it. So like, again, depending on what the function is, you got to think about the risk to the user too, right? Identifying a shark tooth, if it misidentifies it, probably not going to hurt anybody. If you're identifying neurological disorders and it misidentifies it, that can cause serious harm to someone, right? So depending on what you're asking the model to do, you might expect a higher confidence threshold to protect the user from harm. And that's, again, kind of a thing we want students to learn through the curriculum as well.
So for a broken tooth, you're saying you need to show it all of those images as well. And with us, we just see that here's part of the tooth.
Yeah.
You can identify that. So there's nothing built into these artificial intelligence programs for like taking just partial things or something.
So two parts to that. First, yes, we as humans, our brain is really good at inference, right? So we have developed a significant enough training data set in our minds. All those fossils you've picked up, that's your training data set. You've seen a bunch of different broken fossils. So when you find that meg tooth and the corner is broken off, you still know it's a meg tooth, right? The model hasn't experienced as much as we have. So it doesn't know that that broken root lobe is is still a megalodon, it thinks it's now seeing something completely unique, because the most simple thing that typically distinguishes the objects is just the outline of it. So if you're using a pretty simple, small data set, it's going to focus on the most obvious difference between the different categories. And again, in most cases, it's just the shape. But if your data set gets large enough, it starts to realize that other features are important for identification and focuses less on the outline. So for megalodon, that burlette, right? That's often a pretty significant feature for identifying it. So you could, in theory, have a large enough training data set where it starts to realize that that specific feature is the most critical thing, and maybe it could start to make inference from that. But it requires a much, much larger data set to be able to do that. There's also, remember, this is a lesson for middle school students. We're not doing the most complicated version of machine learning that exists in the world right now. There's different forms of kind of like correction to the model. So one way to correct the model is I realize it misidentified something, so I go back and I upload new training data to account for that variable I didn't account for before. But there's other models where you can basically tell the model that it got something wrong. So now it knows to go back and rethink about that picture and maybe look at it from a different vantage and maybe pick up on a different feature. That's called reinforcement learning. And think about it how we learn, right? Like you're in class, your teacher tells you, nope, got that one wrong. Now you realize you need to go back and relearn that, right? So everything that exists within artificial and machine learning is basically just like understanding how people learn and then trying to mimic that in coding. Just it's all logic. It all goes back to logic and reasoning, and how complex our coding is to replicate that logic. So underneath these models, these machine learning models, is called a neural network. And a neural network is trying to replicate the neurons in the brain. And we can create very simple neural networks, like MobileNet in Google's Seashell Machine, which can be processed on a computer, or we can create really, really complex neural networks that require supercomputers to process that data. But we have yet to get to a point where any neural network has the same complexity of the human brain. Our brains are very, very complex. But we're getting closer and closer to that point. Like the models just keep getting more complex. The concept of computer vision or machine learning rather started in the 1950s. So we're hearing a lot more about artificial intelligence now, and you might think that it's this brand new thing. It's been around for quite a while, and it's been improving for a really long time. It was around 2010 that concept of deep learning basically emerged, and we started to be able to train machines to do much, much more complex tasks. I'm probably deviating a little bit too deep into the computer science side of things, but happy to try to explain it.
3D images getting more and more common. Would that help you or hurt you?
It certainly could help, but these platforms only work with 2D. So we would need a different model that can process a three-dimensional image. Obviously, a three-dimensional file is a lot larger than a two-dimensional file. So again, probably not going to process on a laptop. You'll need some kind of supercomputer to process that large of a data set.
Thanks for the chat.
Sure.
Rachel says, excellent idea and presentation. What might be next? If not shark tooth, what topic might this type of project be next?
Sure. So I can tell you my collaborators are planning to submit a supplemental grant to continue this project. I was invited to be a part of it, but since I am now working for Prince George's County Department of Parks and Recreation, this project doesn't really fit within the scope of my job expectations. So I had to turn down the opportunity to stay involved in this project. But yeah, there are people that are going to continue to see how they can develop this curriculum and teach students about artificial intelligence. And I'm sure there'll be others that will build upon the models that we created and continue to create complex things, but it's probably not going to be a significant portion of my career at this point.
So somebody else asked us a bit off topic, but they want to know if you have any good advice for finding neg teeth at Calvert Cliffs.
Go at low tide, look for blowout tides, focus on gravel areas because water sorts things of similar size, right? So it doesn't know the difference between a rock and a fossil. It just is sorting things by size and dependent on the energy of that water. If you're lucky enough, find someone who has private beach access and don't go to Calvert Cliffs State Park. I would never recommend going to Calvert Cliffs State Park if you're hoping to be successful in finding fossils. In terms of publicly accessible sites along Calvert Cliffs, I think Flag Ponds is better for finding shark teeth. If you're more interested in shells, Matawaka Cabins. But ultimately, it is just time and effort, really. That is ultimately what it comes down to. There's no real secret to finding a meg tooth, except being Corey. All right. Any other questions? Or are we ready to talk PGPaleo? All right, let's do it. Okay. So as I briefly mentioned at the beginning, we are an entirely new program within MNCPPC, which is the Maryland National Capital Park and Planning Commission. We're a dual county commission for Prince George's County and Montgomery County, but I specifically am working on the Prince George's County side of things. So I'm sure probably all of you, or at least most of you, have heard of Dinosaur Park before in Laurel. So that was kind of the only fossil site that was really being focused on by the commission. It was established in 2009, but it was being managed by the archaeology program. So not too long ago, there was this discovery of a bone bed at Dinosaur Park, which led to some excavating there for a very long time. There was no excavating. It was strictly surface collecting, whatever just naturally eroded out. Because they started to excavate, they found more things. They got a bunch of press attention. And then the commission decided maybe we should invest more heavily into paleontology. So they kind of split us out and created a parallel to archaeology. So archaeology is a countywide program. We are also now a countywide program. So we are responsible for managing fossil resources on commission lands within Prince George's County. So Prince George's County, if you didn't know, has a really, really diverse fossil record. When you think about fossil hunting in Maryland, a lot of people immediately think of Calvert Cliffs and Calvert County, but Prince George's County actually has a greater diversity of time represented than Calvert County. So we get Cretaceous fossils from the Potomac Formation. That's what we find at Dinosaur Park. We also get Cretaceous fossils from the Severn Formation just before the last largest mass extinction event. We got a message up here. We also get fossils from the Paleogene period, from the Bright Sea Formation, the Aquia Formation, and the Nanjamoy Formation. We even get a few little outcrops of the Calvert Formation in Prince George's County. So there is a lot more fossils than just Dinosaur Park that we could focus on that have basically just been ignored for a really long time by the commission. I know there's plenty of people that have been going to these sites and collecting for a really long time. Finally, now the commission is investing in this program. I would say to more responsibly manage this natural resource that they've sort of been caring for, but not the most efficient way. So our new county-wide program, which again, we're kind of informally using PGPaleo as a little bit more clean way of saying our title. We have three main kind of priorities. Our top priority is natural resource management, improve the curation of our existing collections. So for a very long time, a lot of the fossils that was collected from Dinosaur Park were donated to the Smithsonian and were not retained by the commission. Some were. So we have a relatively small collection right now, but now that we have this new program, we are retaining our fossils and building out a more robust and professional museum collection. So just improving our curation of our existing collection is one of our biggest priorities. We don't actually have a database. We have an Excel spreadsheet for our fossils right now. So big priority for us is to get an actual database to curate our fossils. Our second thing in this category is initiate our county-wide paleontological resource inventory and monitoring. So before we can really manage the fossils in the county, we have to have a more accurate inventory of the fossils that exist. So obviously, we're aware of a lot of different fossil sites on our commission properties, but we don't have it in any form of database, right? So we need to figure out where the fossil resources are, and then we need to monitor those resources to figure out what kind of risks there are to them. Are they rapidly being destroyed because it's a river and it's eroding through the sediments and destroying those fossils? Is it associated with some kind of construction site that's going to destroy them? Is the public going in there and digging up the banks, right? Or is it relatively stable and it's kind of safe to kind of let things happen as they have been? We can't really do much in terms of management until we inventory and monitor. And this is the process that the National Park Service uses. So we're not like reinventing the wheel. We're kind of following the method that's already been being used for basically 100 years by the National Park Service. And then based on that, we want to develop individual site management plans. So how many of you knew that if you're collecting on these park properties in PG County that you're supposed to have a permit? Some do, some don't, right? So it's not easy to find this, but if you look up the management document for Parks and Recreation, there's this policy. Section 20, archaeological and cultural artifacts, fossils. Remember, paleontology was embedded in the archaeology program, so fossils got lumped in with cultural artifacts, essentially. And the policy is no person shall remove fossils, archaeological or cultural artifacts from park property, including blah, 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 except as authorized by permit. So this is embedded in a random management policy document that most people are not going to find themselves. And then on that document, there is no contact information for where to find that permit. The permit can't be found online. So yeah, there's a policy about requiring a permit, but no one knows how to get the permit. So right now, I'm stepping into this position. I'm 3 months into this job. I have to adhere to the existing policy, right? But I recognize that this policy is not really the best way to manage this resource. So what I want us to be doing is, as we're doing this inventorying of our different sites, develop individual policies for different fossil sites instead of one blanket policy of no site can be collected without a permit. So that is the long-term goal. But until we develop these individual site management plans, we have to adhere to the existing policy. And now I'm the person who has to be kind of the bad guy and tell people, I'm sorry, I know you've been collecting here for 30 years, but technically this was a policy that existed the entire time you were doing that collecting, basically. So natural resource management, obviously a huge priority for us now that we are a countywide program responsible for managing this resource. Educational programs is our second priority. We need to continue to implement, expand, and diversify the programming at Dinosaur Park. So just because we've now become this countywide programming, we can't just pause everything that's been happening at Dinosaur Park and focus on that. We still have to maintain what we're already doing and actually do more. So some of the site plans for Dinosaur Park, which are very much in infancy and being developed, are to create an interpretive trail at Dinosaur Park, as well as a new exhibit building. So I cannot tell you a date when these building and trail will officially open, but I can tell you that there are some funds allocated toward this. And I've had a bunch of meetings in my first 3 months about plans right now. So I'm very hopeful that both of these things will happen, but expect it to be a little bit of time. So phase 1 is the interpretive trail. We do think the trail will probably open sometime next year, but it won't necessarily be our final vision of the trail. You'll be able to walk it, but we ultimately want to actually have life-size dinosaur models along that trail, as well as a bunch of informational text and things like that, interpretive signs, but those will probably be added in gradually over time. The exhibit building, we are figuring out exactly where we want it to be. So we're trying to fit it within the footprint of the current Dinosaur Park property, but obviously Dinosaur Park is a fossil site. We can't build over top of the fossil site. So we are limited area in terms of where exactly we can build. And one of our biggest barriers is actually parking. So we have a very small parking lot. There's tons of parking in the neighboring businesses, but they don't want us to use it. So we're trying to come up with solutions for parking right now, because it doesn't make sense to have an exhibit building if no one can actually get to the exhibit building. So there are some logistical barriers that we definitely need to figure out before I can tell you when an exhibit building is going to exist. So we're very excited for this expansion of what's going to happen at Dinosaur Park, but we ask for patience as we figure it out. Establish programs and exhibits at other sites throughout the county. So again, our fossil resource is not just Dinosaur Park. Our fossils are spread all throughout the county, and we want to work with the different existing commission sites to develop collaborations with them to implement programming and create small exhibits on their properties. So we're going to infiltrate all of the different historical sites and have paleontology represented there. And I think a long-term goal will be some kind of like heritage trail where you can learn about paleontology by visiting a bunch of different sites, where we're kind of using paleontology as this kind of marketing tool to get people to visit a bunch of different properties within the commission. Our next one, participate in community outreach to increase awareness of our program and opportunities, right? So not many people know that we've established a new paleontology program. We need to get people to understand that we now exist. We need to communicate existing policies about collecting that haven't really been communicated well, and try to recruit more people to participate in this process, right? So I grew up as a collector, like I told you all at the beginning of this presentation. I don't want there to be this blanket policy where people can't collect and basically inhibit someone from following the similar path that I had, right? If I didn't have those opportunities to get that shark tooth from Calvert Marine Museum and go out and collect those fossils on Calvert Cliffs, I wouldn't be here today. I wouldn't be in this profession. So I want to make sure that we create opportunities for that within Prince George's County. Our third priority is scientific research, right? And I want to emphasize that this is our third priority. The other two come before this. We want to present research on fossils found throughout PG County at professional conferences and at public venues like this. But we really need to emphasize the natural resource management issues as our top priority and our public programming. So our funding, 95% of it comes from county resident taxes. So they are the people paying our bills. So that means that these educational programs should supersede the scientific research that we do, because they're the ones paying for it. And the broader audience is more interested in the programs than the scientific research. And I'm not saying that people aren't interested in the research. I'm just saying more people are interested. We reach more people through those educational programs than we do through a publication. Research is still important, still something we have to do. It's going to inform educational programming, it can inform our resource management, but it is the third priority in terms of these three things. We also will continue to do and need to do, collaborate with external partners, both avocational and professional, to expand the scope of the paleontological research. So our program has 6 staff, but I am the only full-time staff in our program. Do you think I can do research on the entirety of the county from the Cretaceous through the Pleistocene? Probably not. Not efficiently, not effectively, and I'm not going to be able to do everything, right? So our staff is not big enough, nor is any program staff really big enough to do the research entirely themselves. We need to collaborate with other experts and get other people involved so that we can produce more outcomes, more research outputs. So one of the sites that we are focusing on outside of Dinosaur Park is in Upper Marlboro. It is a property that is managed by Patuxent River Park, and it has Paleocene fossils from the Aquia Formation. So this is probably going to be one of our first sites that we work on developing collaborative programming and some small exhibits outside of Dinosaur Park. So the great thing about this is it's a couple of small creeks. One is a dry creek bed. So all of those rocks there are these solidified, indurated sediments from the Aquia Formation, and they're chock full of shells, and they also have some shark teeth in them, right? So we can go out to these sites and talk about the paleontology, doing this kind of nature walk to expose people to this. You also get some small kind of cliff outcrops here where you can get a lot of the shelly material. Down here, you can kind of see this black line through the middle bottom image. That's actually a small fragment of a turtle shell there in that block. And then there's another creek that kind of converges with this dry creek bed that does have water flowing through it. In that creek, we get a lot of fossils accumulated in the gravel where we could actually do sifting for shark teeth. So the goal here is that we're going to do joint programming with Patuxent River Park, where we talk about environmental change using fossil evidence and the modern organisms that live in the freshwater environment today, right? So we got marine fossils. So we can talk about what type of environment did this used to be. Where we now stand was once an ocean. And then we can do the programs that Patuxent River Park already does of collecting modern organisms and talking about how the environment has changed through time. So this is kind of the model that we want to do in as many different sites as we can throughout Prince George's County. Developing joint programming, coming up with these individual site management plans, and creating these mini exhibits highlighting the fossils on these sites. And the Aquia Formation is actually one of the more common ones that appears in a lot of our different sites. So we can tell this kind of connected story at Patuxent River Park, Darnell's Chance House Museum, Tinker's Creek Stream Valley Park. There's a lot of different places, and each one of those was once this same ocean, right? So we've got these diverse geographic data points to tell this story. And obviously, we're going to hit all the different time periods that are present in our county eventually, but it is slow going. So I now wanted to use this as an opportunity to tell you about how you all could get involved with our new emerging program. So we have two different volunteer opportunities. The first one is one that already existed, which is basically volunteering at Dinosaur Park, helping us with our educational programs there, collecting fossils out there, and helping with the curation of those fossils in the lab. I'll tell you, when I came on, or prior to coming on, I had done some work with PG Parks before, and had seen this kind of really large volunteer group, and kind of expected that there's going to be volunteers working here every single day, but basically learned that most of those people are working on the weekends at Dinosaur Park, and very few people come to our main office that's located in Upper Marlboro. It's a lot more remote, more difficult to get to. So we get a lot of help in our educational programs and in the field, but in our collections, we have very few people that actually volunteer and help us out. So we would really love assistance on that side of things. That being said, we'll still gladly take more people to help us with educational programs at Dinosaur Park if that's what you'd like to do, or if Laurel's just the more convenient place for you to go, right? The second one is a new volunteer position that we've just created called the Paleontology Collections Aid. This is basically to help us out with all the things outside of Dinosaur Park. So these big inventorying projects that we're trying to do, we're recruiting people that basically are the ones that have already been collecting on these sites, may or may not have been aware of the permitting policies that we had, rather than, exclude them from the process and say, hey, you don't have this permit, you can't collect here. We're trying to recruit them in as volunteers to help us with these inventorying and monitoring projects. Again, small staff. We don't have the capacity to cover every single site ourselves. We need the help of you all to help us document these sites and to monitor these sites. So if you're interested in helping us just inventory the different fossil sites that exist in Prince George's County, we would love that assistance. If you want to help us in our collections, we would love that assistance as well. We do want to emphasize that this is new and evolving, right? The way it's being implemented now will probably change as we go on, as we kind of figure out what is the best compromise between the commission and collectors and people interested in paleontology, all the different stakeholders, right? It's a tough balancing act because a lot of different people want different things out of fossils. But what I can tell you is that I am committed to trying to compromise and get as many people involved as possible. and not just be this gatekeeper to the fossils. Again, I'm required in my job to follow the existing policy, but I hope to change that policy as we develop these inventories. We do want to note that if you would like to volunteer with us, you have to be at least 16 years old, and you do have to complete a criminal history check because our volunteers interact with the public at times. Our volunteer coordinator is one that many of you know, which is Sarah Quillis, and her email is up here. And this QR code can be scanned. Will take you directly to the applications for these volunteer positions if you're interested in them. So with that, that is all I have for you all today. So I'd be happy to talk to you more about the PGPaleo program, answer any questions you have, and just hang around and chat if you'd like. So a permit, you would email me, and our permit is specifically for research projects. We don't offer a permit for just casual collecting. If you're just interested in casual collecting, we're going to recruit you to become a volunteer with us through the Paleontology Collections Aid Program. Again, have to adhere to the existing policy, and that permit, although it doesn't specify it in there, is exclusively for like scientific research. Doesn't mean you have to have a degree to do it, but you will have to submit a like one-page proposal about what your research project is to get that permit. Yes.
One thing for clarification. So for the Dinosaur Park one, you have to be background checked and fingerprinted as the public. The Paleontology Collections one doesn't have any public interaction. So it's just a background check, which is done online, and I'll send you the link. So if you go through that, determining process, you want to do research, you get approved, you pass the interview with me, then I'll send you the link.
And you're not limited to one. You could do both of these if you want. If you're interested in Dinosaur Park and want to do inventorying projects, we just ask that you register for both because the way we report the volunteer hours is different depending on what kind of things you're contributing. Other questions, comments, concerns? All right, folks. Well, again, thank you all for your time. I'll stick around if you just want to come chat and talk. Thank you.